In this video, we consider complexity. If you have an algorithm, like for example a C program or a Turing machine or a Python program or whatever program you might have, so you have kind of a program. You might be interested not only whether it will hold eventually, you might also be interested in the amount of resources that are consumed by this program. And there are essentially two types of resources that might be interesting for us. The first type of resource is, of course, time. So maybe you're interested in the time your algorithm takes to finish. You're not satisfied with the knowledge that it will terminate eventually, maybe in a million years. You want a better approximation. You want to know more precisely when it will terminate and how the running time depends on the length of the input. And there's another resource, and the other resource is of course memory, which we'll call space. So second resource is space. So that you know how much memory you need, how much hard disk you need to store the data. First, for the time, how do we actually measure running time? Apparently the running time will in most cases depend on the length of the input. If you have a very small input, running time might be small. If you have larger input, running time might be longer. But we are interested in the relation between the length of the input and the running time. Consider, for example, if you're sorting an array, the more elements you have, you expect that the amount of time it takes to sort the array depends somehow on the length of the array. And that's true, for example, for sorting. Simple sorting algorithms have a dependency that the sorting takes n square. If n is the length of the input, then you have n square as running time. If you have better algorithms like quicksort or something, you have n times log n. But okay, how do we actually measure running time? So running time here, our machine model will be the Turing machine. And for the Turing machine, we'll consider running time. And the running time will be, running time is the maximal number of steps on any branch for an input of length n. Because when you start the Turing machine, you have a certain input on your tape, and every time the Turing machine takes a transition, it makes a step. It might move the head or not, but it takes a step, and the maximum number of steps that we have given a fixed input, that's what we will consider the running time. We won't use the exact running time, we'll usually use the big O notation to denote the running time. Similarly, the space. The space is the maximal number of tape cells scanned for input of length n. So what we do is we transition from our program to the Turing machines as our machine model. But in many cases, we'll use more or less informal arguments, how many steps Turing machine will take. So we have two resources, two types of resource, time and space, and we will make a distinction between, on the one hand side, deterministic algorithms. So if it's deterministic, you have for every state you have only one successor, and this successor is uniquely determined. Or if you allow something like guessing. So if you have non-determinism, things might be different. So we will distinguish the deterministic case, and the non-deterministic case. In the deterministic case, that's what you know from a program. You start a program, you know exactly what the output will be. In the non-deterministic case, your program will be allowed to guess. And you might assume that in many cases it might be easier if you allow guessing. Then you will just guess the answer and then later on check whether your guess was correct or not. For example, computing a square root might be difficult, but if you guess the answer and you just want to check whether it's actually the square root, that's much easier, of course. And we'll analyze these different types of algorithms a bit in detail later on. And there are a lot of famous classes we will consider. The famous class here, for example, we'll have a look at is P in the deterministic case and NP for the non-deterministic case, and this P actually means that we have a polynomial time. So here we have all the algorithms that have a polynomial deterministic running time, and NP is not for non-polynomial, but it means non-deterministic polynomial time. Similarly, we have the same for space. We have P space, means polynomial space, and we have NP space. And we'll have a look at the class L, which means logarithmic space in the deterministic case, and NL in the non-deterministic case. Okay, this is more or less the roadmap for the following videos. We'll have a look at each of these classes and how they relate.